Science is such a wonderful tool for advancing civilization. It allows us to learn about all the systems that there are. Specifically here at LCLS-II, where we focus on X-ray science, we're able to look at things now with pulses of a millionth of a billionth of a second, so 10 to the minus 15 second pulse lengths. And this allows you to actually watch how electrons move in molecules.
Welcome to Chelonia Podcast, a podcast about the use of scientific discoveries and technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi. I'm a science journalist, and in today's episode we talk about Xray and laser with Andrew Burrill, head of Accelerator Division at the SLAC National Accelerator Laboratory, California. Nice to meet you, Dr. Burrill. Would you please briefly introduce yourself?
Sure. So thank you for having me, Gabriella. Appreciate it. So my name is Andrew Burrill. I'm a scientist here at SLAC. SLAC is one of the 3 national labs in the US that I've worked at. So I'm a scientist with a broad background in chemistry and physics. I began my career working at Brookhaven National Lab in New York, and then down in Virginia at Jefferson Lab, and then spent a couple of years in Germany at Helmholtz Zentrum Berlin, and now here in California. So my background is in really project management, building big accelerators, and discovery science.
And would you please explain briefly to our listeners what SLAC is and which is the main activity?
Sure. So SLAC is one of 17 DOE Department of Energy national labs, and we are a multi-purpose science lab, but our biggest primary focus is on X-ray science. So we have a very strong program in both X-ray science using our linear accelerator, LCLS, so linear coherent light source, and then as well as using synchrotron light at our SSRL facility. And we also do a broad range of advanced accelerator R&D work. We have plasma wake field acceleration. We have advanced technology for accelerator on a chip. So it's a broad spectrum with a focus on X-ray science.
Perfect. And accelerators are tools used to make experiments on particle physics. What is the specificity of the SLAC National Accelerator Laboratory?
So for SLAC, we specialize in accelerating electrons. So as you mentioned, accelerators can be used to accelerate electrons as well as many heavy ions. But here at SLAC, we specialize in accelerating electrons for the purpose of producing X-rays. So we do this in a number of different ways. Our biggest push right now is doing this with the linear coherent light source. So this is a copper accelerating structure that runs at 120 pulses a second to produce X-rays for both hard and soft X-ray science. And we're in the process of commissioning our new machine, which is called LCLS-II, which is a new superconducting accelerator, which will allow us to run at 1 million pulses per second, which just pushes the boundary of the science that can be accomplished with X-rays.
So, SLAC has a long history in particle physics research, but since 2009, with the SLAC LCLS project, it has been involved also in X-ray research. How did you exploit the existing facilities for this kind of work?
Great question. So SLAC is now 62 years old. The lab was founded as a high energy physics lab. So when they built the lab, they built a tunnel that is a little over 3 kilometers long. And that tunnel then runs down to experimental halls. So we've been able to repurpose that tunnel a number of times over SLAC's history. And this goes back to a comment by one of the early lab directors who said, "How long do you think SLAC will last?" And he said, 10 years, unless we have another good idea. Well, we're 60 years into it, so there have been a lot of good ideas. And being able to reuse this infrastructure has been tremendously helpful. And we've done this for not only in 2009 when they built the LCLS accelerator, which was the first of its kind, and which has now been duplicated a number of places around the world, and it's allowed us to all evolve and continue to push X-ray science. But we've also been able to reuse the middle kilometer of the LINAC for an experiment called FACET-II, which focuses on plasma wave field acceleration, advanced accelerator concepts. And then the first kilometer of the LINAC we're reusing now for the superconducting LINAC. So we will actually have 3 separate distinct accelerators in the 3-kilometer tunnel that's existed going back to the 60s.
Perfect. And now, can you explain to our listeners what is an X-ray free electron laser like LCLS and its difference with respect to a common laser?
Sure. So a common optical laser, like they use, well, in your laser pointer, that's a simplified version, but on more scientific lasers, is an optical cavity is set up. So you have essentially 2 mirrors, and inside these 2 mirrors, you get a light pulse bouncing back and forth, and it gets amplified and then periodically lets bursts of light out. So you use optical pulses inside of a cavity, inside of a set of mirrors. An X-ray free electron laser is quite different. So in our configuration, we use electrons, and we send an electron bunch through a series of magnets. And when the electrons go through the magnets, the magnetic field causes the electron to oscillate up and down. And as the electrons oscillate up and down or side to side, as the case may be, they give off X-rays in the forward direction. And then as a function of how this fancy undulator magnet, as it's called, is built, it allows for these X-rays to be bunched together into bunches and then come out in a coherent X-ray pulse. And this is what we call an X-ray laser.
And now you are upgrading the LCLS to build one of the world's most powerful hard X-ray free electron laser, LCLS-II. How does it work, and which are the main difficulties of this improvement?
So LCLS-II goes from using copper accelerating structures, which are limited to 120 pulses per second, because copper, when you put power into it, obviously heats up. This is how our heaters work at home in many cases. And if you put too much power in, you'll melt it. Well, we don't want to melt our accelerating cavities, so we limit it to pulses. LCLS-II uses superconducting technology. So as the electrons go through the cavity, which accelerates the electrons, instead of it being a copper cavity, it's actually a cavity made out of a material called niobium. So niobium is a superconducting material. So what this means is when you cool it down, and in our case, we use liquid helium. So when you cool it down to minus 273 degrees Celsius or 2 degrees above absolute zero, you enter a superconducting state. So when you put power into the superconducting cavity, you don't lose any of this power into the wall. So superconductors effectively have no electrical resistance. So what this does for us is it allows us to run the RF all the time, so we can accelerate bunches at 1,000,000 pulses per second. So this is really one of the huge step changes from a copper machine to a superconducting machine. So the technology has been, the particular accelerating technology has been used in many places. Superconducting technology is very common. We actually were very grateful for all the help we got from the European XFEL, which built a very similar machine, except it runs pulsed in Hamburg, Germany. And because we have great collaboration with our colleagues there and in France, they were able to help us with a lot of technology, which allowed us to move very quickly in building LCLS-II as a superconducting machine. It also, of course, requires huge partnerships. And one of the things that this project has really allowed us to do is partner both internationally as well as here domestically with, 3 other national labs in the US, Lawrence Berkeley Lab, Argonne National Lab, Fermi National Lab, and Jefferson Lab, so I can't count, as well as Cornell University. So with all these people, that's allowed us to get the machine built in just under 10 years. So that actually addresses some of the biggest challenges. So the technology, we have great, smart scientific, engineering, technical staff. So they love working on these things. So getting the technology to work, they can make happen. Some of the biggest challenges, though, are a single cryo module, which has the accelerating structure inside, and then has all the plumbing that's needed to make everything work, all the cables that bring in power and take out signals. And then everything is done inside of a vacuum vessel. So much like a thermos, it keeps your coffee hot and the outside's cool. Same thing. We keep the inside very cold and the outside is at room temperature. So this is done with insulating vacuum, as we call it, and super insulation. So the real challenges are in making everything come together. I think somebody counted once, and there are something like 14,000 parts inside of a cryo module, and we have 37 of them. And this includes nuts and bolts and washers, but it's an amazing number of things that have to be organized, taken care of, properly put together. And then, logistically, we build cryo modules for this project in Virginia, which is, for those aren't in the US, we're on the West Coast, 3,000 miles away, 5,000 kilometers away is Jefferson Lab. And about 3,000 kilometers from us is Fermilab in Chicago. They build the cryo modules, but then they have to ship them to us. So they put them all together, they test them, and then it goes on a truck. Sounds simple, but this is a very delicate scientific instrument. So we care very, very much about how it is shipped. So some of the challenges are bringing everything to California and then installing it. So then we cleared out something like 600 tons of equipment from the first kilometer of the tunnel. That was a huge endeavor to do all this safely and recycle all the materials, and then being able to then install all the new equipment. So the tunnel itself is roughly 3 meters wide by 3 meters tall. And the cryo modules take up about half that space on the floor. So then once you start to install things, it's a bit like Tetris. So you have a very careful choreographing of putting one piece in while being able to move another piece by it, and then organizing all the work. So the challenges for installation are tremendous in getting all the planning done, everything installed, and then finally getting it all together ready for commissioning, which is the stage we're in now. So we're now to the really fun part, but it's been after years and years of a lot of hard work by a lot of great people.
Yeah, very, very impressive. And do you think that the technology development need for the LCLS-II we have future applications?
Oh, absolutely. So science is such a wonderful tool for advancing civilization. It allows us to learn about all the systems that there are. Specifically here at LCLS-II, where we focus on X-ray science, we're able to look at things now with pulses of a millionth of a billionth of a second. So 10 to the minus 15 second pulse lengths. And this allows you to actually watch how electrons move in molecules. So you're able to, with imaging techniques, watch how electrons move around in molecules, watch how chemical reactions take place. You're able to do things such as develop better catalysts. Of course, we're all thinking about the environment, working on ways to build better solar cells, build better photovoltaic cells, systems that'll help us that way. We're able to do key biological research. We're able to do material science. For example, you're able to put systems under very high pressures and study what happens, under extreme conditions. And there's actually an entire project set up for that. As the machine evolves and as we're able to enhance the capabilities, which is something we spent a lot of effort on, of building new experimental systems and building different ways to, for example, split the electron beam pulse and create 2 different X-rays at 2 different wavelengths to excite a sample and then probe that excited state, all in this attosecond regime, just allows for a great number of discoveries to be made. So there's, I think, a very, very long and healthy life for accelerator science here at SLAC, and with what LCLS-II and the follow-on project that we're starting, which is called LCLS-II High Energy, will be able to provide.
Now we are at the end of this podcast, but Dr. Andrew Burrill, what do you like best about working at SLAC?
The people. So the people, right? We all come to work because we enjoy the challenges, right? And science and engineering is such a great, exciting field because of all the challenges, but it's the people that make you want to come to work. And the colleagues that you have really make it special.
Fantastic. Thank you so much, Dr. Andrew Burrill, for joining us today at this podcast, and thanks our listeners. If you have any questions about today's show, you can get in touch on Chelonia Twitter, and feel free to subscribe Chelonia.Swiss website and be part of the community. In the meantime, stay tuned for our next interview. Thank you again.
Thank you, Gabriella.